So today we are going to discuss about simple harmonic motion. So simply say SHM. So before going to start simple harmonic motion, we should know what is meant by oscillation. So if I consider a simple pendulum, so if I leave my simple pendulum here, from here, it moves towards the mean position, and then it moves from mean position to the maximum displacement. So this is my mean position, this is maximum displacement along my positive x-axis, this is the maximum displacement along my negative x-axis. So if I leave my pendulum from here, it oscillates. So it's a to and fro motion about the mean position, it's called oscillation. Okay, then what is meant by periodic motion? So periodic motion is nothing but it's a to and fro motion about the mean position. The particle should travel the mean position at a regular interval of time. So the time taken by the oscillator to move from here to here, it's a 1 second means. The time taken to reach from here to here also should be a 1 second. Then it's said to be periodic motion. Okay. So all oscillatory motions are not periodic. Okay. So next, what is meant by a simple harmonic motion? So simple harmonic motion is nothing but it's also same to and fro motion about the mean position. The acceleration should directly proportional to the displacement. The acceleration from the restoring force. Actually, if I leave my pendulum from here, actually this pendulum should move to the top. Why it has come back? Because the acceleration due to gravity, it's act as a restoring force, which will pull my oscillator back to the mean position. So I can simply write the restoring force F, which is directly proportional to my minus of x. So this is the definition for simple harmonic motion. I will explain this detail using a spring. So all simple harmonic motions are periodic motions. Okay. So but all periodic motions are not simple harmonic motions. Be careful because it's a to and fro motion about the mean position. The particle should cross the regular mean position the regular interval of time, as well as the restoring force, which is directly proportional to my displacement. So that force which will pull back my system into the mean position. So using a simple example of a spring, I'm going to explain the simple harmonic motion here. So I have a spring attached with body of mass m. So this is my mean position. So I can simply take, this is my maximum, x is equal to plus a, here x is equal to minus a. Sir, what is meant by x, why you are writing x is equal to plus a? So this is called amplitude, it's a maximum displacement from the mean position. So if I pull this spring, after this what's happening? It loses elastic nature, it never come back to its original state. Here we have a minus a, if I compress this mass m up to this point, no problem. Beyond this point, what's happening? It's lost its elastic nature, it's never come back to its original state, right? So now I'm going to explain this restoring force and the simple harmonic motion. So I'm going to apply my, I'm going to pull my spring in the positive x-axis with the displacement, say some 3 centimeter or 4 centimeter, whatever the number. So I'm going to pull my system, pull my mass m to the displacement of x. What's happening? The restoring force, the force from the spring, which will acting in the exactly opposite direction. Agree? So if I compress my spring, it tends to expand. If I expand my spring, it tends to compress. So I pull this mass from here to some x distance. So there is a restoring force. So if your displacement gets increases, the restoring force also gets increases. So this is called your spring force. So now I just want to, I'm going to replace this proportionality symbol by a constant. So f of s equals to minus of kx. This is my equation 1. So what is mean by this k? This k is called spring constant. So this k is called a spring constant. So if I replace the proportionality symbol by a constant, this constant always tells about the nature and dimension of the system. Listen carefully. If I have a aluminum spring, example, okay, case 1, we have a aluminum spring. I am going to pull this aluminum spring by 5 centimeter. the restoring force will be say 5 Newton. Example. The second case, I am going to take a copper spring. I am going to pull my spring for the same 5 centimeter. The restoring force will be same? No. So my force is not only depending upon x, the displacement, it's also depending upon the elasticity of the material. Actually, this spring constant which tells about the nature of the material, or it tells about the elasticity of the material, right? So this is my equation 1. This is the force from the spring, restoring force, which will pull back my system to the mean position. Okay. So now it's going to be oscillate from here to here. It's a to and fro motion about the mean position. So from my Newton's second law, I can simply write my F is equal to m into A. Okay. So I can simply write this A in terms of my displacement, because here my x is the variable. So I'm going to write this in terms of my displacement. So x is your displacement, and I can simply write my velocity equals to dx by dt, and then what is my acceleration? dv by dt. So if I replace this, if I substitute this value here, I can simply write d by dt of dx by dt. My a equals to d square x by dt square. So if I substitute this a value here, I can simply write f is equal to m into d square x by dt square. This is my equation 1. Sorry, this is my equation 2. So if I equate these two, because this is the force from the spring, this is my applied force. So I can simply equate these two. Equation 1 equals to equation 2. Then I may write m into d square x by dt square equals to minus k into x. So the restoring force equals to a force here. This is from your Newton's second law. So I can simply write this equation by d square x by dt square equals to minus k by m into x. Okay. So now I'm going to read this equation. I'm going to define a quantity is called omega. It's called angular frequency. So I can simply write this equation equals to minus of omega square x d square x by dt square. So this is very, very important result here. So I may write this equation. What is my omega here? I can write here omega is equals to omega square equals to k by m. Therefore omega is equal to square root of k by m. So in case if your mass of the system gets increases, your angular frequency will decreases. If the elasticity of the material gets increases, omega also gets increases. So from this equation I can simply write d square x by dt square plus omega square x is equal to 0. So this is the condition for simple harmonic motion. What I told you in the previous, in the starting, all simple harmonic motions are periodic. All period. Okay. All simple harmonic motions are periodic.
Not all periodic.
So if you have a periodic motion, in the examination they will provide the expression for the periodic motion. They will provide x value. They are asking you to confirm whether it is simple harmonic motion or not. Okay. So you have to substitute this value here, x value here. If it is obeys this condition, this equation, then it's said to be simple harmonic motion. Concept clear? If you have any doubt, you can ask me now. So d square x by dt square plus omega square x is equal to 0. So this is the equation of the simple harmonic motion in a differential form. Okay. So now I'm going to, in the next class, I'm going to teach you how to verify this. Okay. So I just stop at this point.